We've all seen SpaceX rockets land themselves. It looks impossible. But what's even more insane is the code making it happen. A flying supercomputer conducting thousands of controlled explosions per second, solving calculus in real time, all to land a 30-story building on a floating platform in the ocean. The rocket landing is mind-blowing, but the software behind it is where things get truly unhinged. Welcome back to PandaProgramming. Today, we are diving into the software, the chaos, and the borderline insanity that makes SpaceX rockets work. If you think landing a rocket is impressive on its own, wait until you see what's happening in the code behind it. Here's where this madness begins. Back in the early 2000s, SpaceX had a problem. Every rocket company on Earth was using decades-old technology, bloated contracts, and hardware that cost more than small countries. So Elon Musk, in a move that can only be described as either visionary or completely unhinged, decided to build rockets from scratch. Not just the engines or the fuel tanks, everything, including the software. And when I say software, I mean the digital brain that has to manage every single thing happening on a vehicle that's basically a flying bomb. At the heart of every SpaceX rocket is a triple redundant flight computer running custom software written in C++ and a bit of Python. This isn't your grandma's desktop. This is a radiation-hardened, fault-tolerant beast designed to operate in the vacuum of space, withstand insane g-forces, and never ever crash. Because if this computer crashes, the rocket crashes. Literally. Into the ocean. Or worse, into a launch pad. Or even worse, into someone's backyard. The flight computer's job is absurdly complex. It has to monitor hundreds of sensors in real time. Temperature, pressure, orientation, fuel levels, engine performance, aerodynamic forces, and about a dozen other things that sound like they belong in a science fiction novel. Then, using all that data, it has to calculate the rocket's exact trajectory, predict where it will be in the next millisecond, and adjust the engines accordingly. And it has to do this thousands of times per second. Not once, not 10 times, thousands. Because rockets don't politely wait for computers to catch up. Now let's talk about the Raptor engines, because these things are monsters. Each Raptor engine burns methane and liquid oxygen in a full-flow staged combustion cycle, which is engineer speak for the most efficient and complicated way to create thrust ever invented. These engines produce over 200 tons of force each. And here's the kicker. The flight computer controls the throttle, the mixture ratio, and the ignition timing of each engine independently. If one engine starts underperforming, the computer compensates by adjusting the others. If one engine fails completely, the computer reroutes everything on the fly. No manual intervention, no emergency meeting, just pure autonomous decision-making happening faster than you can blink. But the real magic, the thing that takes this from impressive engineering to how is this even possible, is what happens during the landing sequence. After the rocket finishes its job and separates from the upper stage, it's traveling at thousands of miles per hour, dozens of miles above the Earth, and heading in completely the wrong direction. It needs to flip around, slow down, navigate through the atmosphere, and land on a target the size of a tennis court. And it has about 6 minutes to figure it out. But the rocket doesn't just fall and then fire its engines. It performs something called a belly flop maneuver. The booster deliberately orients itself horizontally, using its body like a giant air brake to slow down without wasting fuel. This is not intuitive. This is not natural. This is the software deciding that the best way to fall from space is to pretend you're a skydiver, and then, at the last possible moment, flip upright and fire the engines in what's called a suicide burn. The suicide burn is named that for a reason. The rocket waits until the absolute last second to ignite its engines because firing too early wastes fuel, and firing too late results in a very expensive explosion. The flight computer has to calculate the exact moment when the remaining fuel, the current velocity, the distance to the ground, and the thrust of the engines all align perfectly. And it has to do this while accounting for wind, air pressure changes, and the fact that the rocket is essentially a giant pendulum swaying in the sky. If your mind is already melting, go ahead and hit that subscribe button, because we're not even close to done yet. To pull this off, the software uses something called convex optimization. This is a mathematical technique that lets the computer solve incredibly complex trajectory problems in real time. It's not guessing, it's not using pre-programmed paths, it's recalculating the optimal flight path continuously, adjusting for every tiny variation in conditions. If a gust of wind pushes the rocket slightly off course, the computer notices, recalculates, and adjusts the engines within milliseconds. This is why SpaceX rockets can land in conditions that would make other rockets give up and crash into the ocean. And here's something that makes this even more ridiculous. During most of the descent, the rocket is completely on its own. There's a communication delay between the rocket and ground control. Radio signals take time to travel, and by the time mission control sees what's happening and sends a command back, the rocket would already be a smoking crater. So the flight computer can't ask for help. It has to make every single decision autonomously. The software has to be smart enough, fast enough, and reliable enough to handle every possible scenario without human intervention. Ground control can watch, they can monitor, they can bite their nails and hope everything works, but they can't actually control the landing. The rocket is flying itself, and the code better be perfect. And then there's the grid fins. Those waffle-looking wings near the top of the booster. They're not decorative. They're controlled by the flight computer to steer the rocket during its descent. Each grid fin has its own actuator, and the software adjusts them independently to keep the rocket on target. It's like trying to steer a falling skyscraper using 4 tiny flaps, except the skyscraper is also on fire and moving faster than the speed of sound. But here's where things get both hilarious and terrifying. Despite all this precision, all this software brilliance, all these redundant systems, SpaceX rockets still fail sometimes. Early prototypes exploded. Some boosters missed their landing targets and became very expensive artificial reefs. And SpaceX's response to failure is what makes them different. Instead of hiding failures or spending years analyzing every detail before trying again, they iterate fast. They fail, they learn, they update the software, and they launch again weeks later. The code is constantly evolving based on real-world data from actual flights. Every landing, successful or not, feeds back into the system. This is why SpaceX can land rockets consistently now, even though the entire concept sounded impossible just 15 years ago. The software isn't static. It's a living, evolving system that gets smarter with every flight. Engineers at SpaceX monitor every launch in real time, watching telemetry data flood in, looking for anomalies, inefficiencies, or unexpected behavior. After each mission, they analyze the data, tweak the algorithms, and push updates to the next rocket. It's like if your car got better at driving itself every time you went to the grocery store, except the car's a 200-foot tall rocket and the grocery store is outer space. Now let's talk about the scale of this operation, because it's genuinely unhinged. When a Falcon 9 rocket launches, the flight computer is managing 9 Merlin engines on the first stage, each capable of throttling independently. During the landing burn, it might use 1 engine or 3 engines depending on the situation. The computer decides this in real time based on fuel remaining, descent speed, and distance to the landing target. If the software calculates that 3 engines provide too much thrust and 1 engine isn't enough, it pulses the engines on and off rapidly to fine-tune the deceleration. This is not a simple on-off switch. This is precision control at a level that would make a Swiss watchmaker jealous. And all of this, every sensor reading, every calculation, every engine adjustment, happens on hardware that has to survive the launch environment. We're talking vibrations that would shake a normal computer apart, temperatures that swing from -200 degrees to +200 degrees, and radiation levels in space that would corrupt data on a regular laptop within minutes. SpaceX's flight computers are built to handle all of that without breaking a sweat, or without breaking at all. But here's the reality check. For all the software magic, for all the autonomous decision making, for all the real-time optimization, SpaceX rockets are still just machines. They are executing algorithms written by some of the smartest engineers on the planet, running on custom hardware designed to survive literal rocket science, and doing exactly what the code tells them to do. The illusion of intelligence comes from the sheer complexity and speed of the system. When you watch a rocket land itself, you're not seeing artificial intelligence in the sci-fi sense. You're seeing thousands of lines of carefully written code, tested and refined over hundreds of flights, working exactly as intended. And with that, we've come to the end of today's video. If you found this deep dive into SpaceX's software awesome, make sure to smash that like button and subscribe to our channel. We've got more behind the curtain breakdowns coming. Thanks for watching. We'll see you in the next one.